Okay, Darren,
Yeah.
will you please go with that and for the test generation?
Yeah. So good afternoon, everybody. Today we're presenting on this new crossover operator for unit test case generation. Yeah. So first, we just talk a little bit about the authors. These three authors working together at the Software Testing Research Group, I believe, in this university in the Netherlands. They all have quite similar interests on test case generation and search-based software engineering. Yeah, nothing much to say. A PhD student and assistant professor in the research group. So before we delve into it, we just need to have some background on the terms that are used in the paper as well. So these are the three major terms, and some other small terms that we explain in more detail later on as well. So the first to talk about is search-based test case generation. So as the name indicates, it's just you use a search process and try and generate test cases that fulfill certain criteria. So typically we use some kind of coverage like a branch coverage or line coverage, for example. And next, we'll talk about the kind of ways we can generate these test cases. So typically, we use evolutionary algorithms. So these are algorithms that use mechanisms inspired by biological evolution. So genes, mutation, these kind of techniques to try and generate test cases to solve these, in this case, the optimization problem, because you're trying to optimize the criteria that you judge the test cases on. And then we come to an idea of genetic algorithms, which are a type of evolution algorithm that use genetic operators. So what are these operators? They are just ways to guide the algorithm towards a solution. So it takes in a certain number of test cases. In some cases, the operator takes in only one test case. In some cases, multiple test cases, and it combines them in certain ways to do things. So the typical ones we'll consider are selection, crossover, and mutation, which are obviously tied back to the concepts in actual biological genetics. So for selection, it's a way to try and pare down the pool. You select a quote-unquote better chromosome from the pool of chromosomes. So what exactly defines better would be dependent on the kind of operator that you use and split in particular. Then you have a crossover operators where we try and combine at least two chromosomes and try and produce child chromosomes, sometimes multiple, sometimes one child, depending, I suppose. And finally, you have the mutation operator, which just modifies a chromosome depending. So typically, you might modify, for example, the value of an assignment or a statement itself, so and so on. So now we have this in mind. We just talk about a little bit about the kind of crossover operators that are typically used currently in search-based test case generation tools. So this is the single point crossover that works on test cases. So it operates on two parent tests and produce two child tests. And as the picture shows how it works, you just split the tests at arbitrary random points. You recombine them. There's some details that are being left off. Sample. One thing that immediately occurred to you all would be that if you just combine at random points, you might run the risk of having random assignments before initialization, for example, or before variable declaration. So there are also things that mitigate those effects as well. But the basic idea, skipping all the minor details, is that we just recombine the test cases at arbitrary points that we pick. So this will be an example of the single point crossover. We have two test cases here, and then we split them at arbitrary points and recombine them back. So this now we have an audience question. What should be in the test case below here? Just combining these two. Does anybody want to try and answer?
Yeah, good question. So you can, anyone volunteer to have a try. So consider a piece of the code as chromosomes, and we apply the single point crossover. And in these examples, then we know that the single point crossover generated one test case, and what is the other piece? If there are no volunteer, Darren will please randomly point an audience.
Okay, Dorcas, do you want to give it a try?
Sorry, could you repeat the question?
Okay, so as we've mentioned, the single point crossover operates on two test cases. So the two test cases here, we split them at a random point in each test case and recombine them. So we've seen one combination here. So what should be in the other combination?
Int I equals to 6, I equals to I plus 1, then I equals to I minus 1, and then we have the test.
Yeah, exactly that. So that's just the idea, just to illustrate what's happening in this single point crossover. Thanks, Dorcas. Yeah, so with this idea in mind, we can see that we combine the statements in the test case. But what about input data, for example? So in this case, test cases consist of test structures or method sequences as well as input data. And the author's idea is basically that you can also use this crossover idea on input data as well as test case code. and this should help to improve the test case generation process. So now we come to the exact approach, which is this hybrid multi-level crossover. So the aim is, of course, better genetic variation, improved coverage, and fault detection. So these are the criteria by which they judge test cases. So coverage here being typically line or branch coverage, which I'll explain more in detail later on, and fault detection. So how well they can detect problems in a test, in the code under test. So this is typically measured using a weak and strong mutation score, I believe. So it's I'll explain more about that later on as well. So how do they do this? So this new operator combines different crossover operators on multiple levels. So exactly what levels actually later on as well. So implemented in EvoSuite for empirical study. So the overall algorithm for this hybrid multi-level crossover is that we perform the initial single point crossover on 2 parent tests, produce the child test, and then now we do the data level crossover, which is the crossover on the test data that we mentioned before as well. So the idea, when we do crossover example, we need to consider what goes into the crossover. So we talk about it. So what kind of limitations do we have? Can we just cross anything, for example? So this is again another audience question. So we have some questions that lead us to the idea. So for example, do the types matter? Or what kind of methods can we cross? So anyone want to just give it a try?
If there's no volunteers, you can just randomly point on an audience.
Yeah. Xianghui, do you want to give it a try? So you can just try your best to answer this question. Just give your thoughts on the questions here.
Let me think about it for a moment. Can you explain data level crossover very quickly again?
Okay, so we've talked about the abstract idea of a crossover operator. We take in the abstract, we take 2 things, we combine them in some way, and we come up with 2 new things that are related to the parents. So for example, do the types matter? Do you think I can logically combine like a string or an integer together? A string and an integer together?
No, not likely. The type should be the same type.
Yeah, so that's the idea. So that's one constraint we have first, that the type is the same type. And next, do the methods, they use the data method. So if I have 2 methods that take in, for example, a string and int, but one is a constructor and one is a regular method, do you think I can cross over the input data as well?
Not likely.
Yeah, so that's the idea as well. It wouldn't make sense if you combine data from methods that don't have the same purpose, so to speak. So these are the kind of restrictions that the authors identify as well. So not every combination of input data can be compatible. So the restriction that we should only cross identical data types, but they should also be from same types of methods. So constructor, or regular method calls, for example. They didn't actually go into too much detail as to why they think they shouldn't, or what kind of justification they have besides just their intuition. So I'm actually not sure what's the exact justification, but intuitively it makes sense that you shouldn't try to combine data from methods of different types, basically. Yeah, so now we have this. Now with this concept of compatible functions, we can now work on the next part. We should just generate lists of compatible functions. So for every method call, we generate a signature which consists this format, and we iterate over pairs of statements. So the operative statements must be method calls, otherwise we just ignore them. So for those statements that are method calls, we check whether the signatures match from the 2 offspring tests from the first crossover we talked about earlier. We check whether they're both the same type of calls, so either both constructors or both method calls. If they're compatible, then we store them in maps, and we'll use these maps later when we do the data level crossover. So this is the part where we actually do the crossover. So for each signature in the keys of the map, we just retrieve a pair of functions randomly, and then we traverse the parameters, and for each pair of parameters, we just apply a different crossover based on the type. So for the authors mentioned that they've implemented 2 crossovers for two broad categories of variable inputs. So strings and numbers. Numbers being basically like the char, int, double, floats, longs, this kind of number formats. So there are 2 types of crossovers we can apply: the simulated binary crossover and a string crossover. So now we talk about these 2 crossovers here. So first talk about the simulated binary crossover. So it's a recombination operator that's commonly used in numerical problems. And according to the authors and according to some studies, it produces better results for illusion algorithms if you use this crossover compared to just traditional crossover operators. And the long and short of it is we take in 2 numbers, we return a new number, which is the new value for the first number.
Maybe I hope that all the students can still following what I'm talking about. So I think Darren provided a good presentation, but I can make a comment here in case someone missed the point. So here the target is that search-based software testing. Its idea is that it can randomly synthesize a lot of test cases, and I hope that one of the test cases can achieve certain goal. And achieving goal is that we want to cover certain branches, cover certain branches in the programs. And one way to do this is to doing the crossover. That means giving two pieces of code, and we try to cross over these two test cases. And here the goal is that once given two pieces of test cases or two pieces of code, and the code is used for test. And when we apply such an operator on these two test cases, it will end up with some nonsense. So that's the problem. So once these two test cases not compatible, the first half of the first test cases and the lower half, the second half of the second test cases, when they merge together, then may means nonsense. For example, just like Darien says, that the data type may not be compiled, and the parameters may not compile. And basically, this technique is talk about how to address these compatibility problems, right? Okay, I just made a comment here for more people to follow.
Yeah. Just in case if we missed out, so we can also look at the overview. So we've talked about the new crossover operator. It consists of these two portions. Now we're at the data level crossover section, and we're talking about the kinds of data level crossover we can apply. So in particular, now we're talking about the simulated binary crossover, just an overview in case anyone's lost right now. Yeah.
Okay, so better that you can provide more examples. Sorry, I didn't give a comments on your slides when you gave it the URL to me. But
oh, it's okay.
But anyway, let's go through. I'm trying my best to explain for you.
Oh, thanks, Dr. Lee. Yeah, so we'll first talk a little bit about the parameters that are used for this crossover. So with this parameter eta sub c, the distribution index. So this is supposed to indicate how close the new values should be to the original values. And supposedly for higher values, it's closer to the parents. This one's a little bit suspicious because I actually looked at the paper that the author cited for this crossover operator. And I can't seem to find the actual algorithm that the authors are using, which is slightly different from one in the paper. And when I try to fiddle around the distribution index on my own, when I'm just applying the algorithm, it doesn't really give closer values to parents for higher values of this distribution index variable. So I'm not quite sure what's going on here either. But essentially, from the original paper, it's supposed to give closer to the parent's value based on the higher values of this parameter eta sub c. Then we have this generator value, just a random variable in 0, 1. It's just used as choose strategy for generating beta, which is a scaling variable. Use a scale and offset that you add or minus to the parent values to get the new values. So this is the exact algorithm. So we can see the points we talked about earlier, the distribution index, the random variable, and the output. And this is beta, the scaling. So we take essentially V1, the difference between the half of the difference, and you add or minus some scaling depending on whether or not B is true or false. So this is just a way to choose one or the other, so it's a bit more randomized. And basically, just a long shot of it, we input two values, we output a new value of V1, repeat the crossover twice with the parameter switched, we get the new values for V1 and V2, and that's our crossover operator basically.
So here, would you please write two examples for us to better understand, for example, how this V1, V2 appear into test cases? Can you be more specific on that?
Yeah, sure. So if we look at it again, so we look at method calls, pairs of method calls that are determined to be compatible as before in the procedure before, and we traverse the parameters of these method calls, and for each pair of parameters we apply the crossover. So this is only valid for these methods that have for these numerical parameters or string parameters.
Yeah. So here, let me talk about it step by step. So given a test case, it's going to test it's for unit testing, right?
I'm not sure they mentioned unit test in general, just test case generation, but yeah, so it should be unit test case generation.
Test generations, and now you retrieve a period of functions. And what's the relation? And what's the relation between the signature and the randomly selected constructors and methods? And what's the relation?
Okay, so we have, for every function, we have a signature that's supposed to indicate whether they're compatible. So if the signatures match,
let me repeat your explanation and say for every function, there's supposed to be a signature to see whether it's compatible. And it is compatible with what?
Yes, okay. So Every function has a parent. Every function will have a signature generated from that function. And so there are two conditions that have to be met. They have to be met if a pair of functions are compatible. So first is that their signatures have to match. And the second is that they have both have to either be constructor calls or method or regular method calls. So both the same type call. So if these two conditions are met, they are determined to be compatible, and then we store them in the maps.
And what's the point to make two signatures compatible?
Because we can only apply the data level crossover on compatible on parameters from compatible functions.
What I mean is that after we cross over, and that means if we cross over on, let me write it down it. So I still try to digest a little bit. So given two test cases, and this is T1 and this is T2, right? This
Yeah.
T2. And we have a single point crossover. So we want to split these test cases into H11 and H12, and this is H21 and H22, right? And we will cross over. And you mean that if we have two methods here, and after we have the crossover, we have to make sure every function in the half need to be compatible. Am I right?
Oh, no. There might be incompatible functions, and that's okay. It just means that we can't apply the data level crossover on this pair of incompatible functions.
You mean that whether here is we want to detect whether two pieces of code can be crossed over?
Yes, if we can apply the data level crossover.
Apply the data level crossover.
Yes.
Sorry, I may miss again. So the definition and what's the definition? So here the test case crossover, and what's the definition of the data level crossover?
Okay, sorry if I wasn't so clear about this. So the data level crossover applies only to pairs of parameters from compatible functions.
The point is that you only change their parameter, right?
Yes. So this is for generating new parameters based on the previous pairs of parameters in the old test case.
So assuming that we have a method M1, and have another method, suppose here this is T1 and this is T2. We have another method M2, right?
Yeah.
And this method have method A and B, and this have C and D, okay?
Yeah.
The point is that we want to change the parameter constructions in these two pieces of code. Is that a point?
Yes, exactly that.
Okay. Okay, so basically you want to find the type of compatibility. You want to check the type compatibility. Okay. Okay, let's keep going.
Yeah. So thanks for the clarification.
Okay.
So with that idea in mind, so we've talked about the simulated binary crossover. We can give a short example. Most of it's quite technical, so there's not really much to this go into that. It's just a bunch of computation. So we put in two numbers, we use this distribution index. We have three separate cases for each value. Each type of view just showed all the possible outcomes. And these are just the possible values. So the v sub true and sub false are just for indications where the random Boolean variable is true or false. Just give an example of what kinds of values can come out. Yeah. And this value, sorry, this is just for explanation. This value of 2.5 was chosen in the paper, and it's within the recommended range of 2 to 5 that the original algorithm authors gave. So just some insight to why the value is chosen. Yeah. So now we talk about.
You have to raise a question here on previous slides and the previous one. And for here, what does this U stands? So here, so basically, so this is algorithm, right? So input, the input is two variables, and output is the value of variable one. This is a little bit different from my understanding.
Yes, exactly. That's why it's a bit weird because
discussion on their level crossroad. And what is V1 and V2 represents, and how is their relation to the test case?
Okay. So the V1, V2 is just two numbers. So typically V1 will be taken from a method call, so M1 maybe, and V2 from the other method call. And we just take this pair.
V1 and V2 are return type of two method call in respective test cases.
So you're worried that they might be numbers, both numbers, but different number types, right? You're worried about that.
You mean the V1 and V2 are number types, so we're worried about it.
Sorry, I'm not quite sure if I get your question right. What's your question exactly?
The question is that what's the relation of V1 and V2 to the test cases? Suppose we're talking about the crossover, right? The mutation.
Yeah.
So this is T1 and this is T2, right? And what is the relation between, for example, T1 and T2 with V1 and V2?
Okay. So we looked at these methods come from T1 and T2. So we have, for example, like see in your pen, yeah. So we have some method called here and some method called here, and these pair functions, one of them comes from here and one of them comes from the other test case. That's how we get the pairs of functions. And then from the parameters, that's where you get your V1, V2. So in this case, this would be like a V1 and this would be your V2.
So V1 and V2 come from different test cases, right?
Yes, different. So this would come from the methods here.
So for example, there's a V1 defined here and used here, and this is a V2 defined here used here, right?
Yes.
It's V1 and V2. So basically, what you want to talk about is that whether V1 can be used in place of V2 in test 2.
No. This is just a way to using V1 and V2. We generate new values for V1 and V2 to be used in like offspring test case.
Using what in what test case?
The child test case.
In the child case. I'm talking about the child test case. For example,
Yes. So
T1 and T2 are two parent test cases, and V1 is used in a function parameters in T1, and V2 is used in the function parameters in T2. And here I'm asking that you are studying V1 and V2. My question is that whether you're talking about we can replace the definition of V1 and V2 in respective test cases.
Yes, exactly that. That's how they would change
the point is that the T1 now want to use V1 and T1 want to use the variable V2 as a parameters in their original position. Let me be more specific here. Maybe this M called V1. And here another M2 called V2, right? So for the child test cases, we want to define a V2 here, and M1 calls V2, and here we have V1 here, and M2 calls V1. So is that the effects we want to achieve in the slide?
No, sorry. So let me just see if I can clear my drawings first. So if we have this M1 V1 call here and the M2 V2 call, right? So from this pair V1 V2, we generate using the simulated binary crossover a new set V1 prime and V2 prime. So these are the slightly modified values.
Got it. First, you want to check the type compatibility of V1 and V2. Then you use V1 and V2, synthesize V1 prime and V2 prime, and use in the position of V1 and V2 in test case 1 and 2.
Yes. So this will be V2, I guess, prime and V1 prime.
Okay.
Yeah, that's the idea.
Okay, I got it. Let's keep going on.
Yeah. Okay.
Please free to ask any questions here. I try to keep tracking because the students spend time to prepare the slides, and it is supposed to save a lot of time when we read the paper per se. So I suggest that we raise the questions to understand what's really going on in the software testing test generation technique. Okay.
Yeah. So with this, so we've kind of covered the simulated binary crossover and how it works and some example. So next we'll just talk about the next type of crossover, which works on strings, pairs of strings. So this is a similar concept. We have a pair of strings. Each string comes from a method call, one method call, and we want to generate a new pair of strings to use in the next set of method calls in the offspring test. So this is kind of similar to the single point crossover. We pick a point in each string and we just recombine them at this chosen point. So just a simple question just to illustrate how this works. So we have these two words, so lorem ipsum. We split them at arbitrary points here, chosen randomly. So what should be the results of this crossover operator? What should be the new pair of strings? Just a quick question for everyone.
Yeah, anyone would like to have a try. This is supposed to be an easy one. Then Darren, it's your call.
Okay.
You can have the answer.
Okay. Yes, exactly. That's the correct answer. So LOM and ipsirum. So we just recombine them at the chosen points. So it's just straight how this works. So then we should talk about this one here. So now we've covered, what have we covered so far? So we've covered the new hybrid multi-level crossover operator. We've covered the types of crossover you can do and how it works and when it works. So now we have 2 research questions and an empirical study. So the questions that the authors posed are these 2. The first one is, to what extent does it improve structural coverage compared to the single point crossover? So structural coverage here just refers to a branch coverage, a combination of branch and line coverage, which is a way to measure how well a test case covers the method or the code under test. So next will be research question 2, which is how does the new crossover operator impact the fault detection capability of the generated test? So how well the test can detect problems in the code under test. And this is measured using a strong and weak mutation score. So the idea behind strong and weak mutation score is that you modify the methods in certain ways and see if the tests pick up these modifications, whether the tests fail. And the more the tests fail based on these modifications, the higher the mutation score. So that's just a way of testing the fault detection capability of tests.
Yeah. Let's introduce the concept of mutation testing. So if we want to ensure the reliability and the quality of the software, we write test cases. If we want to make sure whether the quality test cases, we want to evaluate or measure the quality of the test cases, and we using mutation scores and the mutation testing. So I hope that that is very basic software engineering concepts. And if you feel free to ask if you are not still a little bit confused.
Yeah. So we'll just keep these 2 research questions in mind, and we'll just go over the results, the methodology of the research or the empirical study first, and then the results. So the first we think about is what classes are used in an empirical study. So what kind of benchmark are we using? So the author selected libraries classes from the Apache Commons library and the Snowball Stemmer library. And the rationale for this is that the new crossover operator works best on projects that utilize lots of strings and numbers, because that's what we can apply the data level crossover to. And so we choose classes where we use a lot of strings and numbers and showcase the ability of the new crossover operator. And so we choose 100 classes from 9 components in the Apache Commons that have numeric and string input data, and 16 classes from this Snowball Stemmer library. So it's just a well-known library for doing things on strings. Stemming is where you pick out the stem word, so the root word from a certain word and use it in certain ways, basically. So this is just covering the kinds of components that they chose for the empirical study. So all numerical stuff, RNG statistics, text processing, string algorithms, logging algorithms, so these kind of things. And then finally, we've gotten the components, and now we're going to choose the classes in the component. We can't test the whole thing because there's just too many classes in these 9 components. So we have to fish out optimal choices for the classes in the components. So they use this particular tool CK, which is used to compute method level and class level codes metrics. And they collect the cyclomatic complexity, so a kind of measure of like how many different paths you can take in the code, basically. And the type of input parameters for each method in the 9 components. And they filter out classes that don't have methods that accept strings or numbers. So this makes sense based on the logic we talked about earlier, that you want to pick out classes that have the most strings and numerical input to show off the new operator. Otherwise, it wouldn't make sense to choose them. So finally, we sort the classes based on their average cyclomatic complexity and pick the top 100 cases for the benchmark. So the ones with the most cyclomatic complexity, I'm assuming. And then we add 16 classes from the previous Snowball Stemmer library for a total of 116 classes for the benchmark. However, not all of them can be used. The authors did a preliminary run EvoSuite and failed to work on some of them. So they just removed those that didn't work, and we have a final benchmark of 103 classes that they used in the empirical study. Yeah, so it's just talking about the implementation. It's just implemented EvoSuite with a new parameter to enable it. It's just some notes from the authors of how they did it. So finally, they did a preliminary study, because when you apply crossover, there's also a parameter for EvoSuite where you can choose how often crossover happens, apparently. And the authors also use a new parameter to indicate how often the data level crossover should happen when the test level crossover happens. So this is what the P is. So if P equals to 0.5 maybe means that when you do a test level crossover, you have a 50% chance to also do a data level crossover. And so they tried out different probabilities.
That they apply data level crossover when a test level crossover is happening.
Yes.
So there's a probability. So when they apply the test level crossover, they will also randomly cross over the data,
Yes.
right?
Yeah.
And I think the data type can be applied even without test level crossover, right?
Yeah, but I think the authors didn't do that from what I can tell.
They didn't do that. They do. Or
Yeah, they do not. Apparently, they only apply the data level crossover when test level crossover is applied.
Okay, so I think I'm not sure the effects, but anyway, I think in this paper they only provide a contribution. The only contribution is that it provided a new crossover operator, right?
Yes.
Yeah, and I'm gonna be interested to see the effectiveness.
Yeah.
Okay, let's keep going on.
Okay. So this is just yes.
Excuse me, sorry. Could you please explain P again? I still cannot understand what is P equals to 1.
P here is that the probability to apply data level crossover when they apply the test level crossover. So according to Darien, in this work, they also provide a very unique a new crossover operator called the data level crossover operator. But this operator will be only applied when they're applying test level crossover. And here the P is the probability to apply data level crossover when the test level crossover happens. For example, when P is equal to 1, it means that as long as there's text level crossover happens, we always apply data level crossover. And the P equals 0.25 means that there is only 1/4 of probability to apply data level crossover when the test level crossover happens. Okay.
Yeah, so
Okay,
that's it. Yeah. Okay, so this just talks about the parameters that the authors used when they executed the test generation using AbleSuite. So this just the default parameters according to the authors. So just some data and some information. I guess mentioned before, the distribution index was set at 2.5, which is within the range of 2 to 5. And apparently this value is recommended by the algorithm designers for SBX. And the search algorithm was the default one for AbleSuite, Dynamos, so dynamic multi-objective search algorithm. So the experimental protocol is that we apply both the default AbleSuite, so without the hybrid operator, and then with the hybrid operator to each class under test and benchmark, and repeat each execution about 100 times with a different random seed each time. So for a total of about 23,200 independent executions on this system. Apparently, according to the authors, it also took about 80 days of consecutive operation to get all the test cases out. So very long time. So finally, after running the test cases, we report the average results, median results across 100 iterations of the structural code coverage, as well as the fault detection capability measured using the weak and strong mutation score. And they use these two statistical methods to determine the magnitude of the result as well as the significance of the result. So this is apparently a standard statistical test to check check whether or not two distributions are really different in a statistically significant way. And then this Varga-Delaney statistic to measure how significantly different, how different they are. And then we see some data now. So what we see here first is that we see first that the box here is a lot longer here than for this one. So this is the single point crossover SBX, and this is the hybrid multi-level crossover. So what this means is that there's less variation here in the branch and line coverage for HMX than compared to SBX. So it means that it's more, according to the authors, this means that it's more stable structural coverage.
Yeah, so but the average is very close, right? The median average is supposed to be very close.
Yeah.
And
but it's more reliable in a sense.
Okay, so it is so improve 2% of the. Okay, let's keep going on.
Yeah.
And what about their significance?
That'll be covered later. So this is the statistical result on the structural coverage. So this is this table basically indicates how it works. The number of times that is statistically better in a significant way. And the magnitude here refers to this hat A12 is the Varga-Delaney statistic. And it measures how significant the difference is. I tried to look at the paper that the author cited when talking about the statistic to see what exactly these categories mean, but I wasn't able to figure out what the categories actually mean in terms of numbers. But the long and short of it is that there's a lot of situations where the hybrid multi-level crossover wins out in a statistically significant way over the single point crossover.
So here, we can see that in majority of cases, they are the same, right?
Yeah.
Okay, the small mean size effect. Okay, so so overall it shows that the HMX is better than SPX.
Yeah. In terms of code coverage, structural coverage.
Yeah, let's keep going.
Yeah. And now, sorry, I have a bit of trouble fitting the table in, that's why it's a bit wonky. But again, we use the same box and whisker plot. We can see that, again, we have a large number of cases for in the same regard, but instead it's time for fault detection capability. So this was the weak and strong mutation score I was talking about earlier. And the statistics show that in 25% of the cases, we have a higher or equal fault detection capability in using the hybrid multi-level crossover as opposed to the single point crossover. And in the cases where it's outperformed, it's only very niche cases coming to the authors.
Okay.
Yeah. So now we just come to the challenges. How do these results look? Are they generalizable? What factors challenge the validity of these results? So there are 4 main points brought up by the authors. So labeled construct validity, internal validity, external validity, and conclusion validity. So these questions, as the author state, we have pointed the initial purpose of the study in the way back in the slides, which is to improve the code coverage as well as the fault detection capability of the test.
I think this slide is very useful for us to write in paper. So here, I think Darien to wiki, right, to Google it. So to have a discussion about there's 4 kinds of validity threats, especially when we finish an experiment. We really cause usually I just write the internal and external validities, and they also have a conclusion and construct validities. Maybe you can, and Darien can quickly go through what these validities are, and yeah.
Yeah. Okay. So the first one, construct validity, is the idea is that we've measured some things from the empirical study. Do these measurements measure the intended purpose of the study? So do they really correlate to the ability of the test to cover the code under test as well as to detect faults in the test, for example? Then there's internal, external validity, whether the internal being that whether any other factors influencing the results that other than the ones we measured. External being are the results generalizable to code in general, for example. In conclusion, we've got these results. Does the conclusion that we draw follow necessarily from the results? So the authors talk about these points in brief towards the end of the paper. So the first one being that the kind of metrics that they measured are well established and used in other studies as well. So it's correlated, it's used by a lot of studies, and it's a good measure of the things you want to measure, which is the ability to cover the code as well as to detect faults in the code. The time-based budget that they use the time-based budget for EvaSuite instead of for example, execution a number of generations-based budget. Yeah, and then internal validity, the only difference between the two approaches is just the addition of the new operator. So there's no other way that any factors can influence the results. So this is clear. And for external, the Apache Commons library is it's a commonly used open source library that's also used in other test case generation studies. So it's the results can be compared to other studies and it's generalizable in that respect. And then finally, the conclusion validity. So in this case, they use the 100 iterations to minimize the risk from randomization. So that takes care of the question of whether or not the randomness of test case generation might affect the results. And then there's also they also apparently follow recommended guidelines for running empirical studies with a randomized algorithm. So they use statistical analysis in this case to make sure that the results are also significant in a statistical manner. So not just by chance, basically. And so the takeaways from it is that even though EvaSuite is a state-of-the-art test case generation tool, there are also new novel ways to improve it, in this case by a data level crossover. And even core parts can still be improved. Yeah, so that's it for my presentation.
Yeah,
Any questions?
I think that is overall it is a very good presentation. So when we are reviewing the EvaSuite, we usually do not. Personally, I will not put too much hope on the crossover, because as long as we have a crossover, the test case will always become incompatible. So the first half of the first test cases, when combined with the first half of the first test case, and then along with the second half of the second test cases, when they combine together, they usually cause an exceptions. So in this case, if there's a crossover in terms of data level crossover, I think there'll be help. but they also conducted such a crossover when the test level crossover happens. So that is kind of my concern. I think maybe a better way. So if I'm the reviewers and if I'm there, I mean, if the researchers, I will further investigating what if we remove the operator of crossover. If I remember correctly, on some researchers have a study showing that a crossover, just removing the crossover, it will brings no harm for the test coverage performance. So that is what I can remember. And also you can see that if we want to go very detailed for papers, we have to we have to understand every mechanism there. And I think we have something to take. Another thing we can borrow is that when the crossover happens, it will definitely generate a lot of exceptions, and how these exceptions can happen. And also, maybe you remove the crossover can even reduce the number of exceptions during the evolution. That is also possible, right?
Yeah.
Maybe let's keep focused on our own FYP projects. Let's try to see, apart from crossovers, even for random mutations, it will incur a lot of new exceptions, and how these exceptions happens, and what does it look like, and what's the best way to mitigate such incurred exceptions, other than we just use evolution to remove them. Whether there's more efficient, and where there's more efficient mutations to incur as less regression as possible.
Yeah. That would be the angle. Yeah.
Okay, thank you, Darren. Maybe let's move to the next presentation. Yufan, would you please share the slides?
Okay. Could you see my screen?
Yes, I can see that. Okay.
Okay,
So
so today
it's more towards the deep learning stuff. So there's always a lot of work to bridging the gap between the deep learning and software engineering. And the Yufan this talk, we're just showing that how far are we to generate code based on requirements. So that is usually a very amazing things. We give the comments, we generate a piece of code. And I think the code pilot has already can do part of that, right?
Yeah. But,
And by the way, does this paper, when this paper published, does Copilot published?
I think no, because
They haven't.
Yeah.
I see.
And it's a journal first paper in XE 21, and it's first in the journal TSE 20, and it's deep learning based program generation from requirements text. Are we there yet? And there are 6 others, and sorry, here the Shen Mingzhou and Zhu Jiaqi is the master student in BIT, and their supervisor is the first other Liu Hui, and Liu Hui is actually a prof at the BIT, and he is PhD in Peking University. And the third other is Niu Nan, and he is assistant professor at UOC, and he is a PhD in Toronto. And I don't know what is the correction between these 2 others. So I found that maybe he is a bachelor in get his bachelor in BIT. So maybe this is the connection. And the Ge Li is the assistant professor at Peking University, and Lu Zhang is the professor at Peking University. And actually, the paper provides some latest information of the others. So if you're interested in the others, you may refer to the paper. And for the research interest, most of them are focused on the machine learning and the software engineering, and some are also have some interest in natural language processing. So that's all for the others. And then we go to what the paper talks about. We have 5 parts. The first, I will talk about the background, and second, we will talk about the new data set created by this paper. And there the others, put forward 9 research questions, and evaluating some published model on their new data set. and then I will show the conclusion. First, the code generation is a very hot topic in current current conference, and the paper there are many papers, and however, though there are many papers and it shows a great result, great blue score in current results, it is even 0.845, but maybe the score is too high to make people believe it, because for the current graph, Google neural machine learning machine translation model, it still only gets about 0.4 blue score. Here is an example. If the reference translation is I know tomorrow is another day, and the general translation is I know tomorrow is a new day, this seems quite a good translation, and the result is still 0.42. And last time I talked.
Why is it 0.42? It seems to be a high. Oh, let me see. Okay, so I got it. So the major decrease lies in the gram 4, right? The 4 gram precision.
Yeah.
But the 4 gram precision is very low. So in this case, the overall blue score will be very low.
Yes, and for the blue score, there are 4. We have 1, 2, 3, 4 gram precision, and for example, here I raised a single question: how many 1 gram and 2 gram in a sentence with like 18 characters or like 18 words? Sorry, maybe we better use 18 words. How many 1 grams and 2 grams in a sentence?
Okay, so this is a question for the audience. And given a sentence consists of 18 words, and how many 1 gram and 2 grams are there in such a sentence? So anyone will try to have a volunteer, serve as a volunteer there. If not, Yufan, you can randomly point about it.
Yeah. How about Xiangling?
Xiangling is not here.
Okay. Maybe let me check. How about Ruofan?
18 1 grams
Yeah.
and 17 2 grams.
Yeah. Yes. So this is what is 1 gram, 2 gram, and 3 gram. 3 gram will be like I know tomorrow as one part, and know tomorrow is as one part. So there is n gram precision, and then you calculate the frequency, and then just to check how much n gram is correct. And the second parameter is brevity penalty. The brevity penalty is just here, and it's just the panel the too brief translation. If the candidate sentence is longer than the reference sentence, it will 1, so there's no penalty. But if the candidate sentence is much smaller than the reference candidate reference sentence, it will have a penalty on the blue score. And for the uniform weights here, Wn is for which blue score you want to compute. For example, if you want to compute the blue 4, then you will just average all the 1 gram plus 2 gram plus 3 gram and plus 4 gram, and average the score. And if you want to compute blue 3, and then you just average it with blue 1 with 1 gram and 2 gram and 3 gram. So that's how we compute.
Questions for brevity penalty. So we can see that on the BF.
Yeah. For example, if the sentence have 4 words and the reference sentence should have 5 words, then it will get a e exponential with 0.8. Sorry, 0.8. So it is less than 1. So it will have a penalty on the blue score.
And what if this is, my point is that if this one is very close to 0, right?
Yeah.
This was very close to 0, and this one is supposed to be E. So it is not a penalty, it's supposed to be a rewarding, right? You get my point.
0.
Suppose R over C is close to 0. It is possible. C.
So that means you use. Let me check it.
So R is the length of generated sentence, right?
No, the reference sentence.
Okay, oh sorry, the reference sentence, and C is the generated sentence.
Yeah.
Suppose the generated sentence is very, very large, right? And then BP will be close to E, right? And E is estimated to 1.7, right?
Yeah.
As long as we generate a huge, a sentence with huge length, and we will get a rewarding by times 2.7.
Yes.
Why?
But if C is very large, then it should be 1. BP should be 1 because it does not go to the second branch.
Yeah. Here.
Very large. Okay, I got it.
Yeah.
So here it means that C will be always smaller than R will always be smaller. Okay, so this one, so C is always smaller, and R over C is always a great. Is the sentence supposed to be 1 over this, right? C will range between 0 and R, right? That means when C is very, very small, and it will become 0.
Yeah.
Okay, the upper bound limits between. I got it. So the upper bound between, and the result between 1 and 0. Okay, that's no problem.
Okay, so
Yeah.
here is the question. So what's the VP value for this example? Anyone can volunteer? The generated translation is I know tomorrow is a new day, and the reference translation is the last this. So just put it into the formula. Let me check. Maybe maybe Yuchen. Yuchen, do you hear?
Hello, yes.
Okay, so what's the BP value for the example here? Here is the formula.
Right, R is the reference, and then C is the candidate. Wow, so the length. So do I need to count the whole length? Is it 1?
Yeah.
5, 6, 7, 8.
So the generated length is, you can compare the two lengths.
Yeah, both of them are 7.
Sorry. Oh, it's 7. So the length is by number of words, is it?
Yeah, yes.
Oh, okay. So is it just 1?
Yeah, because generated length, sentence length is bigger than longer than the reference the translation. So it's just 1. Okay, so any question on the blue score? Okay, so then we go to the code generation based on deep learning. So we always just feed the natural language description to the deep learning model, and want the deep learning model to generate the source code. And here is just the input and output. And the paper evaluate on these 5 approaches. And I will not introduce each method, but you can just have a brief feeling of the approach. The first is sequence frequency. It's just a LSTM model. So you just input the natural language as a sequence and output the code as the same sequence. And the cost to find model actually is just like first to divide the decoding process of code generation to two stages. The first stage is to generate a sketch on the just generate a sketch like a structure, the code structure, and then they generate the variables or the parameters of the structure. So it's just the two stages. They are all sequence to sequence model. So two sequence to sequence model for the cost to find. And the last three is all based on the SG tree, and they are the generate tree to tree model. Okay, so the current data set, the current data set is have three weakness. The first is too small, like the Dingo. The average length of the source code is only 33 characters. And the second weakness is the lack of diversity. And the third is far away from real world data. So the other thought we should have a new data set. And he just collects the data from the programming context platforms like the LeetCode. And he collects all the the questions, or the LeetCode, the requirements, and then removing the duplications, and then collect the correct code provided by the many software engineer, or like many students who attend the contest. And then he has a static checking and cross validation on the code, and then get the data set. And actually, I just watched the video presented by the others, and they said they have some manually checking in the cross validation part. And now we get a new data set. Now it has about 5,000 requirements, and there are 4 types of programming language, and the average length of program is quite long. And you can see here I list the advantage of the new data set. The first is the longer requirements and more programs, longer programs, multiple programming language, and because he has a manually check, so he's valid code, and because it's a context, so there are many students attending the contest, so there are multiple implementations for one requirement. So any question for the data set?
I think here is very clear. Any question here?
Okay.
Let's keep going.
Okay, so we go to the experiment. So because the other thought, all the methods can, no public available deep learning based models can transform the requirement text into programs in general purpose programming language other than Python. So only Python is a common language for all the models. So they just use the Python data here. So you can see he only used the Python data. So now it's about 3,000 tasks. And then he has divided to training, validation, and testing. Okay.
Wait, how to define a task? Task is actually a programming quiz, right?
Yeah, it's just a requirement, a context, a question.
So the Python consists of close to 3,000, and the rest 3 consists of the remaining 2,000, right?
Yeah.
Okay.
Maybe there are some, because for one task, you can write in different programming language.
Yeah, I got it. I got a point.
Yeah. So
So,
I can see this number. The program is.
by the way, have they published such a data set?
Yeah, I think he is on the GitHub.
Okay.
Yeah. So he raised 9 research questions, and let's go over it one by one. And the first is, how accurate are the state of the approach? So he just trained the data set, to train the model on the new data set, and here is the result. And you can see that so every model have a much lower blue score on the new data set. So it seems have a higher blue score on the, the Dango and HS dataset. And so he also checked the mismatch tokens and the irrelevant tokens. It seems higher, very high miss tokens. And it also checks the impact of requirement length. It separates the requirement into 4 groups. And for each group, he tests whether the requirement length influences the blue score. But the results show that no influence actually. So whether how long the requirements, they all get very bad blue score. And he also checked the proposed generate program length would influence the blue score. Still the same. I think still the same conclusion. But
and the length here, the Q4 seems very, it have a very low value here.
Yeah, so other than
that means that the length of the reference programs is very long, it is very large, right?
Yeah. So other than the Q4, but the total blue score is quite low. So okay, so let's go. So for the second research question here, how often do the generative program pass syntactic checking? And I think 2, 3 you can consider at the same time. The first is syntactic checking, and the second is test case. So they use syntactic testing, and you can see that because these 4 models are based on the AS tree. It's based on the AS tree, not based on the sequence. So it can have a higher syntactical correct percentage. However, for these 2 based on the program, they have a much lower score. And for the executable programs, all have a very low score here. But you can see that the SNM model seems the best model here.
How do they define unexecutable program?
They just
suppose the program can be, when a program have a correct syntax, that means it can be compiled, right?
Yeah.
After program can be compiled, and what is the definition of executable and unexecutable program?
The paper said that for the syntactically correct, it means that the variable is defined.
So you mean the static program is not necessarily a compilable program?
Yes. It says that undefined variable accounts for about 68% of the syntactic errors. And for the executable programs, the most error is value error. Value error exception accounts for 72.5% of the exception.
What error? Will you please repeat?
Value error.
What? Value error. What do you mean by value error? So it means,
you use originally is int, because the Python is Python.
Type error, right?
It's Python value error. So because because maybe you do some string operation on the int data structure. So with value error. You use a wrong value here.
Okay, let's keep going on.
Okay. So, and the function incorrect means that you pass the test case and it's 0% for all the models.
Task test cases, okay. Because
Yeah.
all the tasks that I have is actually a programming context tasks, right?
Yeah.
Okay, please go on.
So the paper also want to check whether the generated source code useful for the developers. So they just do an experiment. There are two groups. One group just coding from scratch, and another group that's the modification on the generated code. So a group of students just coding from the scratch, and another group of students modify the generated code, and they found that they almost use the same time. So that means there's no use of the source code. Okay, any question here?
How many developers have they recruited in this study?
How many developers? What means developers?
You mean that how many participants are there in this user study?
Let me check. I didn't.
You can say there are 10 programming tasks there, right?
Yeah, yes, there are 10 tasks.
And those students, and how long does it take for each group to finish? And how long is the time limit for each task? Right.
That I don't think there's time limit. It just calculates for the time for the task. Like here is the 5 minutes and 10 minutes.
It also means that all the students have accomplished the tasks.
Yeah.
And all the test case has been passed.
Yeah, yes.
Okay.
I think
so. So the most difficult task is task 10, right? So it take an average of about 30 minutes to finish the task.
Yeah, yes.
Okay, let's keep going on.
Okay. Yes. Sorry. And he also want to check where and why this model success. So they manually compare, 1,500 generated programs against with 3,000 reference implementation, and they find that most blue score comes from the very typical statement like input, for, and output. And however, though these statements are correct, partially correct, they sometimes misuse the variable or misuse the the structure or the grammar. So the totally correct is a very low, but partially correct is a bit high score.
Okay, let's keep going on.
Okay, so here is an example. And they also want to check whether the model understanding the requirements or understanding the natural language. So they just replace the normal input to a random noise. You can see that if you use a random noise, the program also output the very bad requirements, or you can say it's the same code.
Sorry, so maybe I missed it. So the random noise means that it generates an arbitrary requirement.
Yeah, not arbitrary, that's the random noise. So meaningless requirements, meaningless natural language.
Okay, I got it.
Yeah, so that means
the overall idea is that there's still a long way to go to achieve the code generation based on requirements.
Yes, that means the model even didn't understand the natural language. So, and here is the for the last part. So maybe I have to put into the last page. It talks about how frequently this model output the input, print, and the for in sentence, because these statements are quite frequent in the program. So most generated code contains this for statement. and then they say maybe there's some simple alternative approach. So they want to simulate the evaluative approach, generate the popular statements only. So they just generate the what I said, the input print for in range this statement. So I think this approach is no meaning, because it's not to this approach is not to solve the problem. It's used to just clarify that the current deep learning model even can't beat such a simple approach. Okay. So after they also check whether the redundant implementations help the model. However, you can see that after removing the redundant, they still get a very bad score. So still low blue score. That means we didn't get the redundant implementations also not help. And for the unifying identifier, it is because software engineer or programmers would create some new variable name, and then he just unify all the variable name to one name like var. So they think maybe it's because there are many variable names in the code, so they just want to unify all the variable name. But you can see that the total blue score still very low. So I don't think they are. Oh, sorry. I don't think they are very. They think unifying identifier also make no difference on the result.
Okay, let's keep going on.
Okay, so this is the takeaway. So these are the statistical results of this paper, and the conclusion is that the deep learning models still get bad performance. So maybe they still do not understand the requirements, and most generate popular statements maybe okay. So I think the third conclusion is quite meaningless. And here is the model for the SNM.
So here I think I understand and this is imperial studies, and from the imperial studies we got something interesting. By right we should got something interesting, but actually it's not. The result, the empirical result is not that out of our expectation, right? But one of the things interesting is that this paper showing that the deep learning solutions can almost learn, actually hardly learn anything useful from a requirement, right? And the blue score is largely contributed by some normal pattern like for loop, if, and the input statements, right? So this is what the paper tells us. So anyway, there's a long way to go. And for these specific software engineering tasks, the deep learning approach, AI models, is a very good start. But it is still have a very long way to go. And just borrowing a model, an NLP model for addressing the code problem, it is almost it's almost impossible, right? So this is what the paper tells us. Anyway, it's good to know this. And for Yufan, you can still focus on the comment generation first. And I think we will go to the code generation finally, but we still need to think carefully and what model we're going to choose and how to split and design the tasks to synthesize the code. And we still have a very long way to go.
Yeah, yes.
Okay, is there anyone have questions for the presentation? I think the presentation is quite clear, and I understand Yufan has abstracted away a lot of details. But anyway, as a presentation and such abstraction will be useful for us to focus on the main information conveyed by the authors. Okay, if there's no questions, let's call it a day. Thanks everyone for the attendance.
Okay.
Bye.